Let's get on with tutorial number 12, which is a tutorial on deflection, where I've done an example, this example here, which appeared in your lecture notes. We've got a simply supported beam of 11 meters span, a live load of 6 kilonewtons per meter, dead load of 6 kilonewtons per meter, 550 overall depth, 350 wide. The loads are unfactored. Determine suitable positive reinforcement, and using this reinforcement, determine the long-term mid-span deflection. The amount that the beam is going to sag in the middle with that loading on it. So I've taken the easy way out by using the graphs. I've reproduced the drawings there. It's always a good idea to show them on your calculations, so whoever's looking at it or checking you or marking you actually has easy reference to the question. And there the given factors are. The loading, to work out the ultimate moment, 1.2 G plus 1.5 Q. I've got 1.2 times that there is the mass of the beam per meter, 0.55 times 0.35 times 25 kilonewtons a cubic meter, plus 6, which is your dead load, plus 1.5 times 6, which is your live load factorized. Gives you a total load of 21.975 kilonewtons per meter, or rounded up, say 22 kilonewtons per meter. Very close to that. Work out your moment, WL squared, your ultimate moment, WL squared over 8, and you get an ultimate moment of 332.75 kilonewton meters with that loading. Compute lambda, which is m over bd squared, gives you a factor of 3.8. Get onto your graph. I'm not going to bring the graph out to show you. We've looked at that many times in this course of lectures. P is the steel ratio, 0.0106 for a lambda of 3.8. So our area of steel again is PBD. P times the breadth of the beam times the effective depth, 1855 square millimeters. And we're going to use 3 N28 bars, and if you check in your tables, you'll see that they equal 3 N28s equal 1860 square millimeters, which is slightly more than 1855 square millimeters, but extremely close. So that's all okay. So I've tackled this in a slightly different sequence to the previous one. I've sort of gone elastic modulus, modular ratio, steel ratio, K, etc., etc. But let's go through all of those, as I did in the lecture, which we've just finished. The elastic modulus, as I said, use the 5,000 times the root of the concrete strength. And the elastic modulus for a 32 millimeter concrete, 28,284 MPa. Modular ratio, E for the steel, 200,000 divided by the E for the concrete, gives you an N modular ratio figure of 7.07. Steel ratio is the actual steel area that we've got, which was 1860 square millimeters for those 3 bars. So the steel ratio is AST over BD, 0.0106. We can now calculate K because we've got N and P. There's N, there's P. Pop them into this equation there, and we get a K value of 0.3193. I don't have to grind through this arithmetic with you. I'm sure it's all very elementary to you and to me, so that's fine. Item number 5, find the gross inertia, I gross. The breadth of the beam times the overall depth, and it's 55 millimeters deep, and I'm doing it in meters again. 0.35 meters wide, 0.55 meters cubed over 12, BD cubed over 12, 0.0048 meters to the fourth. Now our cracked moment of inertia is the gross I divided by the distance from the center of the beam, actual geometric center of the beam to the outer fibers. The beam's 550 deep, divided by 2, 0.275 meters, 275 millimeters or 0.275 meters. And that's where that 0.275 comes from for YB. I gross, there it is, multiplied by 0.6, which is a standard factor, multiplied by the root of 32 MPa, 5.656. Gives you a cracked moment, inertia of 0.0592. Okay. Not a cracked moment. That's not a cracked moment of inertia. This is the cracked moment. I apologize. It's a cracked bending moment. The bending moment at the point where the beam cracks, and it's 59.2 kilonewton meters. Because the actual moment using unfactored loads, as we did in the lecture, I've reproduced that here, is we work out a factored load per meter of 16.81 kilonewtons per meter. Popping that into our standard WL squared over 8 gives us a actual moment unfactored of 254. This is the cracked moment. This is the actual moment due to the loading. Now the cracked moment of inertia we work out using part of Branson's formula, this formula there, BD cubed over 12. As done previously, we're using the K value we worked out earlier, the N and the P values, 1 minus K all squared. Gives us a figure of 0.0219 for the I cracked. I've summarized Branson's formula here again. To get the effective I cracked plus I gross minus I cracked, multiplied by the moment cracked, multiplied by the actual moment unfactored load, all cubed. We substitute this in Branson's formula. The IEF, there it is, there. And that worked out to be 0.0021. We substitute that into Branson's formula, the 5W, L to the fourth. The W again is this 16.81 kilonewtons per meter. Okay, 0.0168 times 10 to the fourth over 384 times E for concrete times the IEF, 0.0021. And we get a deflection of 0.0368 meters, which translates to 36.8 millimeters. Now, our standard deflection allowable is 1/250th of the span. Now, span is 10,000 millimeters. Divide that by 250, you get 40 millimeters. Our actual deflection for this beam is 36.8, so we can write OK. And that's it. Thank you.